We are recording. All right, so today, got another action-packed day in physics. This is going to be a lab day. My original plan was to fit in 3 labs. That was way over ambitious. So here's what we're doing instead. We're going to do 2 labs. And having tested this out, last block, the timing actually works out really well for what I want to fit in with just these 2. So we're going to be doing a spring scale lab. I gave you guys this paper back on Monday, so you probably have this. And later on, we're going to be doing this friction lab. So I'll have these 2 pages out, because we're going to be doing these in the next 90 minutes. So does anybody in class need either of these pages? Oh, yep. There. Okay. All right. If anybody else is interested in those, then let me know before we get going too far. Okay. All right. Now, there's one lab page I gave you guys that's this Atwood lab. It involves taking a couple of masses, throwing a string over a pulley, and figuring out what is the acceleration system based on the masses. This is one of my favorite labs, but we're going to postpone that one. What I think I want to do is probably save it for another week, and then I can use that to review forces with you guys. So we might see Atwood come back a couple of weeks from now. Okay. I do want to get you guys some practice doing AP style write-ups. So I'll have you guys do that for specifically for the friction lab today. Let me show you guys the list just to ease your mind about what I'm looking for there. So remember back when we did an AP FRQ that was very similar to that hard ramp up we did in class. Okay? And this is what AP was looking for. They wanted you to name some kind of goal or question. The question today is going to be, what is the coefficient of friction? I put in sort of shorthand here, what is mu? But really, you're trying to figure out what's the coefficient of friction. The 2 surfaces we're going to run past each other are going to be paper and paper. And I went back and amended the scan. There are actually different kinds of friction. So today we'll do a procedure that involves specifically kinetic friction. Okay? You guys remember AP wants you to list measuring equipment as a part, how you're going to gather your data, like a procedure to gather data. Remember, all AP was looking for was probably something in the ballpark of about like 5 bullet points, somewhere there. So if you can condense it to that. Right. After that, they wanted you to say how you're going to use that data to figure out the answer to your question. So in this case, like, what is the coefficient of kinetic friction? Right. Then a conclusion might be a formula or an equation, might be a specific value, like coefficient of friction is like 0.3 or something like that. Right? So I'll put this up later when we get to the friction lab, but just want to preview that real fast. Right. It might be on the opposite side of the Atwood lab. Do you see an Atwood lab? Yeah. Yeah, so Atwood lab and friction lab, I printed on, on the same paper to save some paper, but yeah, lab another day. All right. Okay. So I had some activities lined up in case we had some spare time. We will have about 5 spare minutes at the end of class day, which is actually a perfect time to give you guys time to do the lab write-up. So, okay. Maybe bump the stuff to Friday, maybe. All right, I don't know. Okay. And then I want to remind you guys too, your guys' homework puzzles. AP Classroom, we're going to go over tomorrow. So have that turned in before you guys come to class. Okay. And then college physics, you guys know this too. I want you guys to specifically do these 5 problems. Now, we're starting to get to a routine in this class that I think is working pretty good. So how things have gone the last couple of weeks is, Monday, I introduced some ideas to you guys, so you got some fundamental things. Tuesday's been good for doing a bunch of, or focusing on college physics questions. Wednesday's been good for labs. Thursday's good for AP Classroom. And then Friday, I can fit in whatever I need to clean up in that topic. I'm not going to guarantee every week's going to be exactly like that, but that seems to be a routine that's working out pretty well. So try to stick to that. All right. So I need to grab my attendance. While I'm grabbing my attendance, I realized I never actually wrote down Newton's laws of motion. I've referred to these. We've been applying these. But if you need to digest those, write those down, take a picture, whatever you guys do, then do that while I'm grabbing my attendance. And also have those lab pages out and ready to go. Maybe glance over those. an idea what's about to happen? Okay, I think we're missing Zoe, but we got everybody else. All right, and ready to go. You guys ready? Ready to go? All right, so you guys got Newton's laws of motion. Okay, you know these. Right? Those are the three laws that govern everything in the universe. Well, until you get to quantum, anyway. Right? All right, so agenda, put this to the side. All right. So first thing, spring scale lab. Now this, the intention behind this was to be an exploratory type lab. This is really like 10 mini labs, and this involves some equipment. I've got some lab weights. I've got some spring scales, and the idea was that you're supposed to get your hands on these materials and just see how the forces work. There's some questions that can be confirmed by vectors, like here on number 3 is a really good one. Okay. So, of course, between the quarantine and the time crunch, we're going to do things completely differently, but that'll be right. So just follow along and on this page, and you can see what I'm doing here. Okay. So the first one says weight, suspend a weight on a spring scale. What is the relationship between, say, the mass I'm putting on here and the force? Right? There's one thing I want to tell you guys before we get to going on these spring scales, because these spring scales, they're colored differently to represent springs of different stiffnesses. Okay? So the green one has a very small stiffness, a really tiny force. It's really easy to stretch this guy. The focus screen here. What you guys see online. Okay. The brown one is kind of medium. The brown one's actually pretty versatile. It's pretty good at measuring a lot of things in this class. So it's like a medium stiffness. Good amount of force. Right? And the yellow one's really stiff. It's like, I got probably a lot of force to stretch this. And you guys, well, if you're in class, you got some of these on your desk so you can feel the difference. Right. So yeah, I have to introduce you guys to, again, there's some empty desks there too. Some stuff. Give you guys a few notes here. Okay. Something called Hooke's law. Right? Now, Hooke's law will tell you how much a string will either compress or stretch based on the force that you put on it. So let's say there's a spring, right? This could be a spring, right? It just has some length, right? Like this spring here just has some length. The spring by ballpoint pen has some length, right? Now, I could come along and either push the spring to compress it, or I could pull on it, put a force on it, pull it, and it could stretch it. Let me draw both of those scenarios. Right? Pushing versus pulling. So if I push on it, I compress like that much. So this would be with like a pushing force. Okay? Or I could pull on it, and I could stretch it out like that. Okay? Now, how much is it going to stretch or compress from its original length? Okay? I'm going to call that X. Some textbooks say delta X. I'll just call it X. Okay? And then this one would be stretched by that amount, like that. It's called X. Right. What Hooke's law says is that the force that you apply to a spring is directly related to how much it either stretches or compresses, right? Through the spring constant. Okay? So here's the force on the spring. That's what F represents. Okay? X represents how much it was compressed or stretched. right? And then K is a measure, well, it's called the spring constant. Spring constant. And think of that like a stiffness. Sometimes I'll refer to it that way. I'll say like, what's the spring stiffness? Oh, yeah, Morgan? Yeah, that's yeah, I was about to mention that too. Yeah, so Morgan's bringing up a good point, which is that a lot of textbooks will throw a negative sign here. Let me throw in the units for these before I talk about negative and positive signs. Okay. So force can be measured in newtons. How much its stretch could be in, well, meters or centimeters, whatever, but in general meters. Okay. So stiffness, the spring constant, could be in like newtons per meter. Okay. Now, yeah, what would be up with like putting a negative sign here? What would that mean? Well, the negative sign would tell you something about directions. So if there was a negative sign on this formula, what I would be saying is that the direction it gets stretched or compressed and the force would be opposite of each other. So that would be really the force from the spring. For example, here, you guys see my picture. If I push the spring to the left to compress it to the left, wouldn't, now the force I apply is also to the left, isn't it? Okay. And leaving it positive, that's the force on the spring. That's why I've written here. But if I wanted the force from the spring, like the force from the spring back, right? Newton's third law of motion. Okay. In that case, that would be opposite direction, so I would include a negative sign. Okay. The same idea with stretching. So here I'm pulling it to the right, rightward force, so I also stretch it that much to the right. Okay. So the force on the spring and how much it stretches, that would be a positive relationship. But do you think the spring is also pulling back with some force? Would be, right? If I was holding in equilibrium, those forces would be equal and opposite, wouldn't they? Newton's third law of motion. Yeah. And since it would be pulling back of the direction it would stretch, then so it would be negative for the force from the spring or positive for the force on the spring. Okay? Yeah, so that's a really good point to bring up because, yeah, you open up a textbook, a lot of times they'll slap a negative. Like, what's up with that negative? Okay. You guys good there? Okay. Right, so there's basic spring mechanics. Okay. Now we're kind of ready to break out the slab paper. Now, this is a really informal lab, so you know, mostly just to see like how do springs work, you know, how do forces work. Okay. So first one says pick some different weights and see what's the mass and what's the force rating on these things. Okay. So I got a bunch of weight friends here. Got this guy's 200. This guy's 200 also. I got a bunch of 200. Okay. Well, let's do at least 3 of these. Right? Maybe I'll pick the smaller ones are kind of harder to measure. Okay. So let's do these 3 amigos right here. I got a 200 gram guy. So specify this would be in grams. The 200. I've got a 500 gram guy. I've got a 1,000 gram guy. Okay. We'll just do those 3. What's the force rating? So for the small guy, I definitely want the green scale. Okay. Right, so if I lift it, right, now there are actually 2 readings on the scale. Now I'm doing this all on my projection. Obviously, this is an awkward point of view. So I'm going to do wherever it naturally hangs to. I'm just going to stop this with my finger and then turn this so that you guys can get the reading. There are actually 2 sets of readings on the scale. One side it says grams, and the other side it says newtons. Now, since we're measuring force, and it would be a force to measure at some distance, wouldn't it? Okay. Oh, by the way, guess how it's scaled evenly, like 1 Newton, 2 Newton, 3 Newton, 4 Newton. That's really strong evidence that this is a direct relationship. Double the force is going to double how far it goes. Triple the force, triple how far it pulls. Okay. Are we interested in the Newton side or the gram side? What do you guys think? Newtons, because Newtons measures force. Okay. So that's what we're actually using for the spring scale. What the grams could represent is as long as you're stuck at the surface of Earth, what mass would produce like a stretch of so far. But if you took this to Mars, the grams would be completely useless. Okay. So the newtons would still work, wouldn't it? Okay. So these are like Earth scales. But yeah, let's do newtons. So this is, okay, I'm going to stop this, turn this so you guys can see it. It's reading almost 2 newtons, almost 2 newtons. So since this is really an exploratory lab, just getting the idea down, I'm just going to 1 sig fig that guy and just call it 2 newtons. Okay. All right. How about this guy? Right. 500 grams. Right. Right. Now, turn that to kilograms by dividing by 1,000, multiply by 9.8. You should get the predicted force value. Right. Let's see what the measured force value is. Right. Stop this, turn it. It's like right at 5. It's like a shade under 5, like right at 5. So I'm going to call that 5 newtons. Right. These spring scales are not super precise. It even has something interesting printed on it. It says not legal for trade. So I don't know, maybe it's like some law like want to measure the weight of bananas or something, it's like, it's not that accurate. And then how about the 1,000 Newton guy? Now, the 1,000 Newtons, I can't use the grain scale anymore. This 500, or what did it say? Right. The 500 grams 5 Newton guy maxed out this grain scale, right? Because it only goes up to 5 Newtons. Right? So we need to switch over to the Brown scale at least to grab the weight of the 1,000 gram guy. Right? So 1,000 grams. Right, so I'm going to stop this right here. Just turn this so you guys can see. It's reading it like right at 10 Newtons, right at 10 Newtons. Okay. Theoretically, it should be 9.8 Newtons. The scale is shown about 10 Newtons, and a lot of times we round to about 10 Newtons anyway in this class. Okay, right. All right, so what would this look like on this graph? It says draw a graph of F versus M. So I need to specify a force is going to be in newtons. The mass is going to be in grams. Right. Got the mass going up to 1,000, so we scale it accordingly. So 0, 500, 1,000 grams. Okay. The force goes up to 10 newtons, so I'll scale that accordingly. Let's go 0, 5, 10 newtons. Okay. So for the 200 gram guy, that was 2 newtons. That's about right there. 500 grams and 5 newtons, right there. 1,000 grams measured a weight of 10 newtons, right there. Right. Oh, look at that. I should have had you guys predict ahead of time what would that graph look like, but you would have predicted that anyway, right? Okay. And when what is the slope of that line? Would it be the free fall gravity on the planet, right? If you were to drop it, right? Weight divided by mass should give you free fall gravity. Okay. So FYI, it should be something like that. About 9.8 or 10 meters per second squared. Right. The next idea I want to get is, what if you have a single weight? Let's say, say this big boy right here, and I take 2 scales and I shift the weight so that they carry weight. Maybe it's not split half and half, or maybe it is for one of the trials. Right. What would that look like? Right. Now, this is kind of comparable to if you stand on 2 legs, and you could distribute your weight evenly, right? Or you could split it so that like one leg carries more of your body weight than the other leg does, something like that. Okay. All right, let me grab these gold scales for. Oh no, oops. All right, never mind. Let's go. Oh, brown scales. Brown scales are perfect for this one. Sorry, should have been taken. Okay. All right, so I've got these 2 scales. Right now, I'm trying to distribute it pretty evenly. All right. Let me stop these exactly where they are. Shift this so that you guys can see. It's reading really close to 5 and 5. It's like 5.1 and 4.9. So it's really close to like 5 and 5. Okay? That adds up to 10 newtons for this 10 Newton weight. Okay? Now, what if I shift this a little bit? Like, what if I put more weight on the left side? Let's see what these scales would do. Okay? Okay, so I could shift it like so. Okay, ooh, perfect. Let me stop this. No, just write some good numbers. All right, stop it right there. Shift it. You guys can see it. See where it says 6 versus 4? Ooh, 6 versus 4. The left side was 6. The right side is 4. Right? What if I shift it even more drastically? Right? What if I take the left scale and take it all the way up to 8? Right? And then stop the. Okay, we get to 8. Then stop it there. Stop the other one. Let's see what they came out to be. So it was 8 versus 2. That's what it came out. 8 versus 2. As I'm turning them, they're shifting a little bit. But when I was holding them vertical, it was saying 8 and 2. Okay. And finally, what if I go the other way? What if I put, say, 7 newtons on the right side, and I'll let the left side naturally go to whatever it would be. Stop these, turn them, and look at that. Well, when I was holding it vertically, it was showing 7 and 3. That was the split. So it was showing, so go 3 and 7. So 3 versus 7. Okay. You guys see over and over, it totals to 10. That's because as long as I was holding it at rest is an example of equilibrium. Does equilibrium necessarily mean at rest? No, it could be going constant velocity. So if I was pulling them up or pulling them down at constant velocity, they should get the same numbers. Okay? But all the forces had a balance. So 10 up and a total of 10 down. Okay. What does this graph look like? Well, I need to scale this up to 10. So let's go. These would be in newtons. 5, 10. And then same thing here. This would be in newtons. Got 5, 10. Okay. So there was a point that was 5 and 5. there was the 6 versus 4, so that lands you right about there. There was 8 versus 2, that lands you right about there. And then there was 3 versus 7, which lands you about right there. That, guess what that relationship's going to be? Okay. So that, see, if they're adding up to 10 all the time, then I'm getting a straight line relationship like that. That's good. Okay. Now this next one is the one that involves like vectors and sine and cosine. Right, you guys ready for that? Okay. So what if I start from something very similar to what I had before, just taking everything vertically. Right? Well, I'll throw in a third scale. Right? And then I start to stretch these out and make a Y shape. You guys see that Y shape? Right? And I make it closer and closer to a T. Ooh. Right? Let's do some hypothesizing before I actually do this. Right? Do you think that bottom scale rating is going to change throughout this? It shouldn't. It should just read the actual weight that's going. Right? What about the top scales? Do you think the top scale is going to change as they change it from this vertical shape to closer to a T shape? Right? I wonder how they would change. Let's pull, right. I'm actually going to drop down to the 5 Newton guy for this guy. So use a little bit smaller lab weight. Right. Let's get this rigged up. Right. Now for this one, I'm going to change this a little bit. So I'm changing my camera. Just missing this detail in class. Okay. I'm moving my camera over. I'm going to do this in this lab space out here. All right. Is this in the picture? Yep. There in the picture. Okay. Right. Then you guys in class can see what I'm doing. All right. I need this, and no, I know what I need to do. Good. Let's start with three Brown scales. That's what we'll start with. Okay. So hook this guy here. Okay. So it's rated 5 Newtons. That's all fine and good. All right. How about? You know what? I think I changed my mind. Let's go with the big guy anyway. I know what I'm going to do. We're going to switch to his gold scales later on, and then right, we'll really get a fun effect going on. Right? So I did bring in the 10 Newton guy. Right? So this is the guy that weighs 10 Newtons, and indeed, the bottom scale is rating 10 Newtons, and the top scales, they split it half and half. Right? Right now, they're rating 5 and 5 Newtons. Okay, so we got 10 Newtons on the bottom guy and 5 and 5 on the top ones. Okay. Now, I made this table a little bit weird too. So, okay, force on the bottom spring will be 10 Newtons. There's a column that says each top spring. That's not the most scientific way to do this. Really, I should do a column for each one. But as long as you distribute it evenly, you see how in my pictures it's all symmetrical, right? So let's just keep it symmetrical all the way down, and then each was showing 5. Okay. Now that angle. Okay. See, you guys online probably. Right, that angle, see how I'm measuring that angle with respect to the vertical? Right, that very last picture shows it. The angles with respect to that dashed vertical line. Okay. So a perfect T shape would take that angle to 90 degrees, wouldn't it? So if the total top angle is 180, right? So on this paper it would be like 90. Right, so I'm going to make it closer and closer to that shape. And I wonder what's going to happen to the force rating on my scales as I do that. So I've got this protractor hanging here so I can read the angles. Remember, I'm measuring the angle with respect to the vertical, which is like this red string that's hanging down. Okay, that's my baseline. Okay, so as I pull this out to like a Y shape, okay, let's take this up to a 30-degree angle. Okay, 30 degrees measured with respect to that red string. Right. All right. So the bottom scale didn't change at all. It's still reading 10 Newtons. The top scales bumped up to about 6 Newtons each. Ooh, so they actually went up a little bit. So at 30 degrees. Okay, like this. Okay, you guys got that? Right. And then you guys online, I want to see that. Okay. So 30-degree angle for that defined angle theta. Bottom spring didn't change. The top scales went up a little bit. They bumped up at about 1 Newton each. Okay. What if I make this even more pronounced? Okay. What if I take this all the way up to a 60-degree angle from the vertical, which would also be, isn't this well, I don't know if this is quite the right word, but equilateral. Right? You see how there's just like a perfect Y shape? There's 120 degrees between any two of the scales. Okay? Back on Monday, I asked you guys, could you figure out a way to draw 3 forces in equilibrium with each other? And this is one of the possibilities. And in that case, they should all be the same force, shouldn't they? It's perfect equilateral Y, right? Like this. Okay. And that would be 60 degrees relative to the vertical for right? But let's see if that's actually true. So the bottom scale is reading 10, and indeed, each of my top scales is just barely maxed out at 10 newtons each for exactly that shape. Yeah, so that actually worked out perfectly. So 60, 10, and 10 is what I'm looking at. Right, something like this. Okay. And then, well, if I want to take it above that, since I just maxed out those brown scales, I need to switch out these two top scales with the gold scales. Remember, the gold scales are really stiff. Okay, so they'll let me measure higher values. This brown scale is maxed out, but he's not changing, so fine with that. All right. Let's make this closer to a T shape. Right? What if I try to make a T? So let's take this angle all the way up to, let's say 80 degrees. I'll get it really close to, can I even do that? Yeah, looks like, okay, this gold scale's will, oh boy. All right, hold on. Let me switch out one of these guys. This guy's a little stiff or something. Something a little off about that guy. Okay. Bring in a different gold scale. Okay, yeah, I think these are better. Okay. Can I get this to like an 80-degree angle? That's really close, right? It's almost maxing out these gold scales. They're each reading about 45 newtons. Wow, okay. And it takes a lot of force to hold it like that. Okay. So up at an 80-degree angle from the vertical, okay. The bottom scale didn't change at all. The top scales went up to about 45 newtons. About, right. Let me switch my camera for you guys online. Get us back. Okay, so I'm done making my measurements. Now I need to go figure out how am I going to make sense of this, analyze this. Okay. What conclusions can I draw about forces from this? Right, so I've got this graph, the force of each top angle, or sorry, each top spring, which is like this column here, it's like your y value, versus your x value's angle in degrees. And remember, if you did have a perfect T shape, this angle would be defined as 90 degrees, right? And that's as far as you can go, right? Let's plot these points. Now my largest force was 45 newtons, so let me scale that accordingly. 10, 20, 30, 40, 15, so 10, 20, 30, 40, and then 45 newtons is going to be straight above that. So at 0 degrees, it was reading 5 newtons. Or each top spring was reading 5. At 30 degrees, each top spring was reading 6, which is not much more. Okay? At the 60-degree angle, which is a special angle, it's like the equilateral situation, it was all the way up to 10, which on this graph is not much higher. Okay? And then at 80, it was at 45. Oh man, that's way the heck up here. Okay, you guys see these points? And I got a couple of questions down here. First question is, as this angle, this defined angle here from the vertical approaches 90 degrees, another way of saying that is you're getting closer and closer to a perfect T shape. What is the force in each top spring approach? Who thinks they can figure out what's the answer to this particular question? If I did make a perfect T shape, what would the force be in each top spring? Here, what's happening at 90 degrees on this graph? What shape does this look like? Looks kind of shallow, starts out. It does increase, but it's kind of shallow. And then all of a sudden, bam, goes way up. So as you get closer and closer to 90 degrees, what's the force approaching? Infinity. Josh was saying infinity. Good call. Yeah, it's going to go up forever. Huh. So could that angle actually reach 90 degrees? Could you actually make a perfect T shape? You could not. Yeah. So, and that's consistent with what we've done over the last few days with forces and vectors, because let's think what that would be if you did make a perfect T shape. Let's say you had a spring scale like that, spring scale like that, one straight down. Okay. So there would be a weight pulling down, but from this node right here, where they all come together in the middle, right? Like this node, where they all come together, there would be no vertical component to hold everything up. Yeah, so that would be impossible. Right? Versus here, if I take each of these forces from this node point and I break them into components, right? You see how there's a, I'll make like sideways triangles. Here's left, up, right, up, versus down, right? And then same idea here. It's got left, up, right, up versus down, right? Is it true that the vertical components, this plus this, have to balance out with that vertical going down? So the two up guys have to add up to the down guy, right? And if the down guy isn't changing, it was 10 newtons all along, that means the two vertical guys have to add up to 10. So this would be, these vertical components are 5 and 5 all the way through. 5 and 5 to add up to 10, 5 and 5 to add up to 10, right? But the geometry of these triangles is changing. They're getting skinnier and skinnier triangles, which means the hypotenuses are getting longer and longer. And in fact, at a perfect T, it would go to infinity, okay? So one material consequence of this is that if you're ever walking across the floor of a building, like we're on the second floor of a building right now, okay, the floor below you is going to compress just a little bit to handle your weight. That's how materials work. Right? It'd be impossible for it to not. Oh, vertical chain. Got the chain gang. Let's do that. So got scale, weight, scale, weight, scale, weight. What is this going to look like? This is, we sort of talked about this yesterday. We're talking about, I remember this coming up. Okay, so let me switch my camera so you guys online can see the chain. Right. Found out last class this works better if I start from the bottom. So get some 200, 200, 200. Okay. Okay. So I just picked 3 weights. They're 200 grams each, which means they should be about 2 newtons each. Okay. Gonna chain them like this. So my brown scales are my go-to scales because, like I said, they're pretty versatile. All right. Yeah, you guys can see that, right? All right. And what I want you to record on this, I said label the forces from each of the scales. Okay. Let me label these weights too. So this would be massive: 200 grams, 200 grams, 200 grams. Okay. So online, just so I'm recording what the masses were. Each of those masses is 200 grams. Hold on. Okay. Yeah, there you go. Okay. And then what are the force readings in the scales? Okay. So the bottom scale, and you could probably predict even before I tell you the numbers. Okay. What do you think the bottom scale is rating? 2 newtons. It's just holding the bottom on 2 newtons. What do you think the middle scale is rating? Yeah, 4 newtons. Okay. That's just a shade over 4, but it's about 4.5, maybe 4.5. Okay. And the top one, what do you think? 6 is a good call. I'm actually reading 7 here. And I think where the extra newton is coming from is the weights of the scales themselves. That makes sense? Right. So the scales themselves have some weight, which is not negligible compared to the weights of these 200 gram masses. Okay. So the actual recorded values, the empirical values go straight. The bottom scale was 2 newtons. The middle scale was about 4.5, and the top one was about 7. Okay. All right, follow-up question here. Let's say there's this heavy metal chain suspends a weight. Maybe it's been in a warehouse for decades, some abandoned warehouse. It's rusting over. Which link in the chain is most likely to break first? One near the top, one near the bottom? Yeah, there you go, one near the top. Because anything near the top is responsible for holding everything below it. Anything near the bottom only has to hold stuff below it, which is not nearly as much. Okay? Now, AP could totally ask you a question related to what we just did, but they might put it in a different orientation. They might have something like a horizontal train, right? Like if I take this and like, sure, like let's say the engine in the front is pulling everything behind it. Okay? Now, in that case, would the engine have to apply a force to every single thing behind it? It has to pull everything, doesn't it? Sure does, right? What if you're closer to the end, like closer to the caboose? Don't you only have to pull everything behind you? Which is not going to be nearly as much, is it? Ooh, yeah. So, yeah, if you ever see like an engine pulling a whole line of train cars, or maybe blocks, because people like blocks and stuff. Yeah, think about that. Think about what we just did. That could just be oriented horizontally, possibly. Okay. Oh, the 6th one. Okay, so I'm keeping the exact same setup, but I'm just going to throw in one more scale in the middle. Say, what's going to happen to that scale rating in the middle? So, get my camera turned for guys online again. All right. So, back to the chain gang. The chain gang is going to get a middle friend. Grab the screen guy because I think the screen guy's going to be able to handle it. All right, click this guy. Right. So let's some stuff here. All right, there we go. Got something like that. Right. Oh, whoops, I lost the weight. So this guy on the bottom. Okay. All right, so the bottom one is still reading 2 newtons. That's all fine and good. Okay. Now the middle ones, let's see if I can get it to split like half and half. It's gonna do that. Gonna let me? No. All right. Well, okay. It didn't distribute evenly. So I'm looking like I think 1.5 versus 2.5. What is that? 1.5 versus 2.5. That is up to 4, right? And the top one is reading like about 7.5. Okay. All right. So here. Okay. So the readings went. The bottom scale. These are all 200 grams again, but 200 grams, 200 grams, 200 grams. Okay. The bottom scale is reading 2 newtons. The middle scales, what did they say? It's 1.5 and 2.5. Right. Now that adds up to 4, right? I did want to split half and half, so maybe like 2 and 2. And the top scale was reading like 7.5. Like that. Yeah. Right. So the idea that you can walk away with this is that by including the extra scale, that force actually splits, actually distributes. Right? And then each scale has a whole list. Kind of like if you had a monkey chain with your friends. Right? If you have like 2 friends in the middle, then they could help each other out, holding everybody below, right? Okay. So if you have like a weight with like lots of strings on it, the more strings, the more that weight's going to distribute. Okay. That'll be important for next week. You guys see that funny contraption over there by the wall with those red pulleys? Right? I'll show you how you can. Okay. Wow. Next week we'll do a mechanical advantage lab. I'll show you guys how you can, with a very small force, lift something very heavy. It's going to be related to this idea right here. Oh, yeah, Jared?
So, if you were to, I guess if you, the 200 grams, for example,
All right.
if you had that hanging from a spring, you were to push up on it to try to get a force of 1 newton on the scale, would you have to push up with the force of 1 newton? Or would it be...
Okay. So you're saying if I push on with 1 newton, can I do something like that?
Well, I mean, like, if you push up on it until, push up on the weight that was hanging from the scale, to get it to 1 newton.
Grams on the scale, and then you push up on the scale until the meter says 1.
Yeah, you exerting 1 newton.
Yeah. Okay. So let's get a heavy guy for this one. Right. Let's say I have 1,000 grams, which is pretty close to 10 newtons, which is going to max out this Brown scale. So this Brown scale right now is being maxed out at 10 newtons. Okay? Yeah. If I push up on this, true. Let's say I push up with 3 newtons. Now the scale should read how much? 7. And in fact, it does. Right. Well, here's where it was stopped when I held it vertical. It's holding at 7. Okay? If I push up even more, my hand would be holding more of the force. If I push up with 8 newtons, doesn't the scale read 2? Right? Yeah. So I could do that. That's pretty similar to what we just did, and also maybe this one. Yeah. So forces can split like that. Yeah. The more force that your hand applies, the less force the spring scale has to apply. Right? Yeah, they add up to the total weight. Because if you did a free body diagram for that, it's really a free body diagram question, isn't it? Right? Yeah, let's say you had a mass of, let's say this guy's 1 kilogram. Right? So free body diagram, FBD. Kind of side note here, right? So this thing has a weight pretty close to 10 newtons. It's like 9.8 newtons, but let's round that to about 10. Okay? Now, if it was just holding from a spring, then I would have an upward force from the spring of 10 newtons. And that's actually what the spring scale is reading. Okay? But what if you're also supporting it from your hand? Okay? Here's how you can do, we've got 2 upward forces, right? How can you put those right on top of each other? What AP says you can do is you can go from the center mass point, make a little check to the left, and then go up, and then make a little check to the right, and go up like this. Okay. So I might say the force from the spring scale might be, for example, 7 newtons, and the force from your hand could be 3 newtons, so that this guy and this guy add up to this guy. Yeah, so it holds it in equilibrium. Okay. Yeah, so there you go. That was a great question there. All Now, some of these on the back, some of these we might do more thought experiment style, but I'll do as best I can in this little space in front of me. Okay. So what if I have this 5 Newton weight on this Brown scale, and I want you to accelerate this. You guys remember doing like elevator type problems? I threw you guys at least. Oh, actually, I think we did 2 elevator type problems yesterday from the college book. So what if I accelerate it up? Now, the obvious way to accelerate it up is to pull it up faster and faster. Right? What do you think is happening to the spring scale rating when I do that? When I pull it really fast? You think it jumps up really high? Right? Yeah, it does, because this thing has inertia, it wants to lag behind. So if I'm pulling it faster and faster, then yeah, this is going to breed a force that's greater than the weight of it. Okay? So the force rating would increase. Okay? Now, there is a trickier way to accelerate it up. Okay? That does not involve moving up, speeding up. What's the other way to accelerate it upwards? Move it down, slow it down. Yeah. Couldn't this thing be going like from the 5th floor down to the 1st floor if it's an elevator, and then slow down to stop? And as soon as it stops, don't I have to, just for one instant, maybe like 1 second, don't I have to apply a huge upward force to slow it down to stop? Yeah, because this thing has inertia and wants to keep going down. I have to apply an upward force to slow it down to stop. That would also be increasing upwards. It never moves upwards. But it does accelerate upwards, right? So 2 options. Could be moving up, speeding up, or it could be moving down, slowing down. Okay? Vice versa, accelerating down. Now, the obvious way, of course, is to make it go down faster and faster, right? And if I do that, isn't that something akin to maybe like, actually in extreme, it would be perfect free fall. What if I just take this thing and I drop it? It's just falling off a cliff, like, oh, it's just like all loosey, right? Is there going to be any force rating at all? There would not be. I should you guys know that's consistent with a handy dandy formula that we derived yesterday. Now, AP does not give you this one, but sometimes this is helpful to use, like tension in the elevator cable. That's kind of what we're doing, isn't it? Okay. What if you accelerated down at the full rate of gravity? So this was like G and then accelerating down negative. That's what's G minus G. 0. So when the tension is be 0, if you just drop this off the cliff, right? See how that's consistent? Okay. All right. So anyway, one way or another, this is going to decrease. And that was an extreme. Pure free fall would be an extreme example of that. But sometimes if you take things to extreme, you can get an idea of some general principle. Right? Now, there is a trickier way to also make it accelerate downwards. What's the tricky way to do it? There you go. Yeah, moving up but slowing down. So if there's an elevator pulling this up, and then you reach your destination floor, maybe it's the floor, right? And you bring it to a stop. Right? Now, what's physically happening with spring scale is that you guys can't really see this, but well, we just put a video recording here. This will sort of work on video. Okay. Maybe you guys can kind of see it in class. Right? If I bring this up and bring it to a stop, you guys see it jump up, right? Say like it lost some force reading just for a moment. Jumps up very briefly. Okay. Say like it gives some slack in the gives some slack in that tension. Some slack in the spring. Just bigger. All right. Next one, hanging over an edge. So what if I took a string, connected these 2 spring scales, have a mass down here, and then I accelerate this back and forth. Okay? Now, this is actually the exact same idea as what we just did, except I oriented it a little bit different, and I explicitly mentioned all 4 scenarios. Okay? So we're going to do a thought experiment version of this. You guys ready for a thought experiment? Okay. Just because I'm trying to shave a minute off class here, right? So we're cut a couple of corners just for quarantine times, right? If the top spring is moving left and speeding up, so I'm taking this and I'm pulling, I'm like jerking it to the left, faster and faster. What do you think would happen to the force rating? Increase, yeah, increase. Right? Same idea as pulling up faster and faster, right? What if you move it to the left but slow to a stop? What's going to happen to the force rating? Yeah, decrease, right? Because if you kept it going left at constant velocity, there would be some force rating. And then by slowing it to a stop, you're like putting some slack in it, just for like 1 second, maybe, something like that. It's gonna drop a little bit. Okay? All right. What if you are moving this top guy to the right faster and faster? What happens to the force rating? Right. Let's take that to an extreme. What if I was holding this in place? You guys imagine there's a string here. Right? It's connected to the scale, which is connected to this weight. Right? So I'm just taking that diagram, this diagram right here. I'm physically constructing it out of string scales. You guys see that, right? Right. So what if I'm holding this in place? Like, oh, this is really heavy. I'm having trouble holding this in place. And then my arms get really tired and I just let it go. If I just let it go, wouldn't that be a case where it would just accelerate like, off the table? Wouldn't that be the Brown scale would move to the right faster and faster? Right? And in that case, if I just let it go and it just like fell off a cliff, what's the spring reading? 0. It would go to 0. Now that would be an extreme case. So in general, you could say the force reading decreases, right? Decreases. And then finally, to close this off, when the top spring is moving to the right, but slowing down. So what if I have this moving to the right and I jerk it to? It's gonna bump up instantaneously, just for like 1 instant. Yeah. So then now we're back to something like that. Okay.
Sounds like Grace.
Yeah. Right. All right. You guys good so far? Oh, what's this in the chat? Okay. Yeah, it's just a. Okay, so yeah, you're good. Just got a technical issue going on there. Oh, well, I see what you're talking about. Right. What just happened? All right, hold on, guys. I got a technical issue to take care of here. Google Meet's acting weird. Where's my camera options? Did this disconnect? I think that's what happened. All right, we're good to go. Okay, yeah, thanks for letting me know, guys. This would have messed up my recording, so we're good. Yeah, thank you. All right, so next thing. All right. Okay. Friction. Okay. No, the next lab we're going to do is going to focus on this. So yeah, let's do these 3 parts. This is a warm up to what we're about to do later. Okay. So I've got some masses of some objects. Let's pick here. Yeah. Let's just do 2 of these. Right. We're going to go with the 500 gram guy and the 1,000 gram guy. Right. So 500 grams and 1,000 grams. Okay. What's the force to lift and the force to drag? Right. There's a specific reason I'm only doing 2 objects right now, and that's that all these other objects. See, well, what's the difference between like here? If you see these 3, you guys see what 2 of these have in common? I mean, they're all different masses, they're all different weights, but these 2 are painted, and this one's not. Right? So when we're talking about friction, we're interested in 2 different materials dragging past each other. And if I drag this paint across this paper, I should get a different result from this bare metal drag across this paper, right? That's why when we get to the actual friction lab later on, I've got these guys wrapped in paper, so I'll have paper on paper technology, right? So it's all consistent, right? But for now, let's just do the painted ones. Okay? So that's the logic behind this madness. Okay? So what's the force to lift this guy? So just stop this right here, show you guys. I'm looking at 5 newtons to lift the 500 gram guy. You guys see that? Now, what's the force to drag it across paper? Okay? Now, I should specify. Oh, actually, I did say right here. Slide it across at constant speed to say constant velocity. Okay? Let's see what this would be. It is reading, like almost exactly 1 Newton. That's what I'm reading. Hold on, just got stuck there. Yep. And so drag it across at constant velocity. I'm looking at 1 Newton. Okay. How about the 1,000 gram guy? Okay. Oh. Grab the weight of this. So that maxes out the Brown scale at 10 newtons. Show you guys both. I just stopped it where it was. Was it about 10 newtons? Pretty much 10 newtons. Right. What's the force to drag this across the paper? Right. Looking at, okay, at constant velocity, I'm looking at about 2.5. Well, yeah. 2.5, it's bumping up and down a little bit, maybe down to 2, but it's kind of settling on about 2.5 newtons. Okay. All right. Now, they should be the same paint pulled across the same paper. So there's some material property that's related to that. It's called the coefficient of friction. Right. No, specifically because these surfaces were sliding past each other, it's called kinetic friction. And this is an idea we talked about. So let's do a free body diagram.
think about what's going on there. Okay. I got some lab weight. There was an applied force. I'll say F sub pull. Okay. There's this thing had a weight. There's a normal force. Okay. And if I just drew that and walked away, would that be equilibrium? It would not be, which means it'd have to be like not constant velocity. So what else do I need? Friction force. And this needs to be the exact same magnitude as the applied force, the pulling force, so that it puts it in equilibrium. Now, if you just had this and you didn't know any different, could you know if it was in motion or not? No, it's ambiguous. It might be stuck, in which case this would be static friction, or it might be sliding at constant velocity, in which case this is kinetic friction. Now you guys know this kinetic friction case. Coefficient of friction in general is the ratio of these two guys. Friction force compared to normal force. Right. Now, you guys see obviously normal force is equivalent to weight. So if you know one, you can know the other. As long as you're on a flat surface. On an incline, that all goes out the window, but something to do with cosine or something. Right? But for a flat surface, these would be the same magnitude. Right? Okay, so going back here, could you guys figure out pretty quickly what the coefficient of friction is between this paint and this paper? What's 1 over 5? 0.2. What is 2.5 over 10? 0.25. So the coefficient of kinetic friction, I should say, therefore is about 0.2 for the first one, about 0.25 for the second one. Okay? Those are pretty common values for a coefficient of kinetic friction. It's somewhere there, about 0.2, 0.25. So if you ever see something like that, it's just the ratio of these two columns. Okay? In general, does it require more force to lift something or drag it? What do you guys say? Lift it. Right? In this case, it was about 4 or 5 times the force to lift it. Right? Do you think that's a hard and fast rule? Is this always going to be true? Not necessarily. So coefficient of friction, remember there are 2 kinds. So kinetic is always less than static. Right? It always takes more force to get something to break the initial friction than it does to keep it sliding. Right? It's going to be more than 0. So in our example, it's like 0.2, 0.25, somewhere there. It's usually less than 1, but it doesn't have to be less than 1. So for example, if you have brand new tires on a car and there's a newly paved road that's dry, it hasn't rained for a few days, you could get a coefficient of friction that's greater than 1. It might be like not much bigger. It might be 1.05 or 1.1. And what that would mean is that it would actually be easier to lift the car than it would be to push it across the surface, right? So that's a really rare case, but it could happen. Okay? You guys good there? All right. These next 2, we're going to do thought experiment versions. So thought experiment, and same thing with the thought experiment. So buoyancy. What if I took this thing and dipped it in water? So we're just going to make up some numbers just to get the idea. Cut a few more corners here. What if I had a 200-gram guy or a 500-gram guy? This could be in grams. Okay. To lift it, it should be like 2 newtons and 5 newtons. We've grabbed those numbers earlier today, so something like that. Okay. Now, what if I dip this in water? What do you think that would happen to the spring scale force? It would decrease. Do you think it would decrease for different objects? Like here, how about this? What if I had 1 kilogram just densely packed like this versus 1 kilogram of ping pong balls? Right? Guys, if I dip this in water, is that spring scale rating going to go down very much? Hardly at all. So, all right, well, okay, I've got 2 newtons and 5 newtons. So in the 1,000 grams, call it 10 newtons. Right? So maybe to 9 newtons, but probably not even that. Right? This might be like 4.5 newtons. This one, you might not see barely any change at all. Now, these are just made up numbers, right? Thought experiment, right? I'm just making up some numbers, just to give you guys the idea. Right? But what if I switch this out and went with a kilogram of ping pong balls, right? Guys, if I had a kilogram of ping pong balls and I did the same thing, rest them in water, are those ping pong balls going to float? Yes. Isn't that buoyant force going to carry all the weight of the ping pong balls? So what would the scale rating be? 0 would be, right? And for here, it'd be barely changed, might be like 9 newtons. Right. So maybe it's something to do with the density, like really dense materials. Maybe you don't get as much of a buoyant effect as compared to non-dense materials. Right? But here, so yeah, just hold on to that idea for now. But let's look at the free body diagrams for those cases. So in air, you got the weight down and the force from the spring scale up, versus a buoyant force would be something like this. This would be your free body diagram. If AP asked you to do a free body diagram for the situation, this is what I'd do. I'd have a force from the spring scale that was a little bit less in magnitude than the weight, so they could also have a buoyant force, okay, where the spring scale force plus the buoyant force added up to the weight. Okay, that'll be the free body diagram for that type scenario. Okay, guys got that? Okay. And then finally, what if you were to put this weight on the spring scale and swing it around in a circle? What do you think would happen to the scale reading if you were swinging around in a circle? Do you think it would increase?
Yes.
Yeah. So in general, I would say that the swinging weight would be, the swing force reading would be greater than it just hanging at rest. Okay. Now, that's always going to be true if you're swinging it in a horizontal circle. I'm leading up to a counter example, actually, okay? One that would actually break this rule. Right? So if you're swinging in a horizontal circle, so that it may be like a cone shape. Can you guys imagine a cone shape going on? Okay. In that case, I know this is 100% true all the time for that case. Here's how I know, because of trigonometry. So there's a downward force from the weight. There's a sideways force. It's called centripetal force. It's actually holding in a circle. From a centrifugal point of view, it feels like you're being thrown out, but really it's pulling it into a circle. Right? So I drew these vectors backwards. Oops. Okay. So it has the spring scale has to hold up the weight, has to hold it in because of the centripetal effect. Right? So the overall effect is the hypotenuse of this right triangle, and that's going to be greater than the actual weight of the thing, isn't it? You see that? Okay. Now, counter example time. Can you guys think of a case where this would actually be backwards of the truth? Can you swing something in a circle and actually make the force reading decrease? How about if you swung it in a vertical circle? Here's the top of the circle. Here's your spring scale. Right? And what if you're swinging around kind of slow so that it just barely made it around the circle? Do you think the force reading might be pretty small at that point? Yeah, so no, that would be not sustainable. It would only be true for this top portion of the circle. But yeah, anyway, there's a counter example. Okay, you guys got that? All right, so that was really just an exploratory type lab. Now let's do something a bit more serious. All right, you guys got ready for spring scale? Or sorry, friction. All right, friction. Let's see where we are in time. All right, yeah, we're done, right? All right, now friction. We're actually going to do two parts with friction. Right? Now, in both cases, I'm interested in figuring out what is the coefficient of friction. And I talked a little bit about that already because we just did the warm-up with friction, right? In fact, the first part I'm going to do is very similar to what we just did. Right? Then the second part to get to, I'm going to use a really weird method of I'm going to put this on a desk. I'm going to tilt the desk to some angle until it breaks the friction and slides down at constant velocity. Okay? You guys got that? Do you think that angle that it breaks the friction has something to do with the coefficient of friction? Because what if there was no friction? What if it was like an air hockey table? Okay, you guys imagine air hockey table? This is a puck just kind of floating around. If I tilted the desk even to like 1 degree, wouldn't it immediately slide down? Right? So I bet that angle is somehow related to coefficient of friction. Have you guys figured this out? All right. Now, this lab, this is the one I told you guys to. I'm going to have you guys do an AP style write-up. Only do it for one of the parts. Okay, so pick your favorite part. If you like the sliding part with the spring scales, or if you like the tilting the desk part, you'll have about 5, maybe 10 minutes at the end of class to write this up. Right? Or you can get a head start if you want to do this along the way. Right? So AP is looking for this style format, and you guys saw this in the FRQ that we did. Right? There's some kind of question we're trying to address. I did shorthand version here. What is mu? I should spell this out. What is the coefficient of friction between, right? And then here's where I coded all these weights and paper so that I have consistent materials. Because remember, this is a material property, right? And then I oopsed also last class. I realized, I shouldn't say coefficient of friction. I should specify, because there are 2 different kinds of friction, right? There's the static, have you broken the initial friction yet? In which case it can build up to that number. It's actually an inequality as a formula, right? Or is it kinetic, in which case the surfaces are actually sliding past each other, right? And we'll focus on the sliding, okay? That's the way I'm going to approach this lab. I'm looking for 2 surfaces to actually slide past each other. Kinetic friction. Guys good? Right. List what measuring equipment you need, which the measuring equipment is going to be different for each of these. Right? you think I need spring scales to measure the pulling force, right? What about the angle that I'm tilting at? What tools do I need to measure an angle? Oh yeah, one of these, a protractor. Right? So whichever part you pick, keep that in mind. Okay. Remember, AP wants you to write a procedure of how you're going to go about using that equipment to gather your data. So refer to the equipment. Remember what AP is looking for is maybe like 5 steps somewhere in there, plus or minus, right? 5 bullet points. Maybe you have 3 bullet points, maybe you have 6, but somewhere there. Then tell AP how you're going to use whatever data you acquired to figure out the answer to your question. In this case, the question is, what's the coefficient of kinetic friction, right, between these two materials, paper and paper, right? And the way that we're going to do that is make graphs, right? That's a really good go-to method to solve things for AP. You say, oh, I'm going to make a graph. I'm going to put this variable on the vertical axis and this variable on the horizontal axis. And maybe I'm looking for slope, maybe I'm looking for coordinate, maybe I'm looking for area, right? Depending on what the setup is. Okay? And then your conclusion, in this case, the coefficient of friction is some number, right? Or for AP, they might want a more general thing like the coefficient of friction is going to be like the slope of this line on this graph. Okay? You guys got that? Okay. You guys know what you're doing for this? Okay. And yeah, if you work a pretty good pace, and I work a pretty good pace, I think most of you guys will be able to get that in the grade tray before you walk out of this room, so we won't have to worry about that home. All right, so let's start with the first half. And I've intentionally not written out any directions here because I want to see if you guys can follow along and come up with that out of your imagination. But I'll take you guys through the table. All right, so what are the weights of these things? So I'm going to grab this green scale for the small weights. Okay. Let's go ahead and measure the values. Okay. So this guy's measuring really close to 0.5 Newton. So 0.5 newtons. Okay. Then what's the force to drag it across the surface? Ooh, okay. It's registering, but just barely. Can you guys tell? Okay. See if I put no force on it at all. Actually, it's not even exactly calibrated right. The 0 mark isn't exactly aligned with 0, but if I pull it, it's about, it moved about 2 notches because it actually starts from like -1 notch. Right. Can I calibrate this a little bit better? Okay, there it is, zeroed out. Right. Yeah, it's about right, constant velocity. Yeah, okay, well, it's still calibrated like at -0.1 newtons. So two notches is about 0.2 newtons, isn't it? Okay. And then right here, coefficient of friction just is the ratio of those two. Guys, what's 0.2 over 0.5? 0.4, something like that. Okay. All right, and then I guess ideally you'd have like 2 sig figs, but I might just do 1 sig fig through. Right. All right, let's go the next step up. Right, this guy weighs 1 Newton. Right, I'll show you guys. Right, I'll stop it where it was. It was stopped at like right at 1 Newton, 1.0. Right. Maybe the weight itself is almost a Newton. I put on the paper and it came up to like 1 Newton. Right. What if I drag it across at constant velocity? Right? Oh, I should mention static just as a side note, right? Well, hold on to that idea. I'm going to do that with larger weights. Let's just focus on kinetic right now. Okay? So drag it across at constant velocity. It's reading about 0.3 newtons, maybe about 0.3. I think that's what I'm reading. Right. So divide those out, you get like 0.3. Right. Let's move up to the next heavy guy. It's this guy right here. This guy weighs 2 newtons. Let me show it to you guys. I'm reading 2 newtons right here. So 2 newtons. Okay. And let's see what the drag force is. The drag force is, it looks like it's hovering between 0.5 and 0.7. Oh, it's getting stuck on something there. So it's getting really big. Right. I'll call it about 0.6. Right. Oh, that's the exact same ratio as what we just got before, isn't it? Okay, so it also divides that to about 0.3. Right. Right. Now the heavier guys. Okay. Now here's where I want to make 2 extra points that you might be tossed around in your mind. Right. One is that you might wonder, well, does the surface area have anything to do with anything? Right. Because some of these weights are small, have a small surface connection And then some of these weights are a lot bigger, have a much larger surface area contact between this paper and this paper. Right? Does that matter? It turns out it doesn't. What matters is the force, which is like the weight of the thing. Right? And if you have more area that you distribute that force over, you would be decreasing the pressure, but not actually the force between the two things, and also not the normal force. So yeah, so the surface area ends up canceling out, makes no difference. Another thing you might be wondering is, what about the static friction that we've been forgetting? So if you pay real close attention, let's see if I can make this work. Oh, that's on the gram side. Let me switch to newtons. Right? It should actually require a little extra oomph to get it going. So right now, see, it's stuck to the paper. Right? So this is static, static, static. I'm up to like 1.5 newtons, still hasn't moved. I'm up to 2 newtons, still hasn't moved. And so it looked like it got up to like just over 2, maybe like 2.1 before it actually bumped, right? But to keep it constant velocity, see how it's hovering around, is that, I think it's hovering around 1.5, is that? 1 okay. Sometimes it's a little more, sometimes it's a little less, but it's hovering around 1.5. Oh, how much does this weigh again? Forgot to get the weight. Okay. So the weight is, yeah, it's 5 newtons. It just maxes out the Green scale. So the weight is 5. The drag force at constant velocity was about 1.5. Right? But remember, it was like 2.1 just to get it going. So 2.1 over 5 would tell you static friction. Sorry, the coefficient of static friction. Right? 1.5 over 5 tells you coefficient of kinetic friction. This lab, we're just focused on the kinetic part. Right? You'd want to specify that in your directions, right? In your lab write-up, specify that we're doing kinetic friction. Right? So that can, oh wow, that actually also comes out to 0.3. Promise you, I'm not fudging the numbers on that. I just actually, all right, it just comes out to that. Okay. All right. So yeah, we've got 3 in a row where it's like the same number. I mean, ideally it should anyway. Ideally it should come out to the same coefficient. So yeah, this is working out really well this class. All right. And then finally, the big guy. All right, so for the weight, I need different scale. So let's break out the Brown scale. Right. And let's see, this is, okay, let me stop this where it is. Show you guys, it's reading like right at the 10 mark. Right, so it weighs 10 newtons. Okay. What's the force to drag it across at constant velocity? That's interesting. It's only saying, right, well, now to get it going, you have to bump it up like over 3, but once I get it going, actually it settles at like 2.5. It's hovering a little bit more, a little bit less, but it's kind of hovering around 2.5. So this came out to like 0.25. Right? All right. So what's the average of these 5 numbers? You guys know how to take an average, right? So add all the numbers up. Then divide by 5 because there are 5 numbers. So we should get a middle value from this. And the middle value we're getting is like that right there, 1.3. Right? Oh, right, you guys got that? Right. So yeah, so regardless of what the weight was, the 2 surfaces were both the same materials, paper and paper. Pretty consistently, it's the same number over and over, isn't it? Right. What would F pull versus weight look like? So that title tells you which variable goes on which axis. Here's F pull. We're measuring in newtons. Here's the weight. Also measuring in newtons. Okay. And let's see, the pulling force went up to 2.5, so I have to scale that accordingly. Let's go. I'm gonna do this. Wow. Okay. It's called 0 newtons, 1 newton, 2 newtons, 3 newtons. Oh, yeah, actually, that's perfect. That'll work. Okay. So I've got every 5 notches is a newton vertically. And horizontally, it needs to go up to 10. So maybe every notch could be like a newton. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that'll fit all my data right there. Okay. So let's plot these like Cartesian coordinates. So when the weight was 0.5, the pulling force was 0.2. Ooh, that's right there. Okay. When the weight was 1, the pulling force was 0.3. When the weight was 2, the pulling force was 0.6. Then we got 5 newtons, the pulling force was 1.5. And for 10 newtons weight, the pulling force was 2.5. Take a look at those points. They land up pretty well in a straight line, don't they? Like a direct relationship. You see that? Okay. So here's the pulling force. Here's the weight. Okay. What is the equivalent magnitude to pulling force? That would be the friction force, at least in equilibrium it would be. What's a force equivalent to the weight? That would be the normal force, the support force from the paper. Okay. And therefore, what is the slope of this line equivalent to? What physical property? How about the coefficient of kinetic friction, right? So, and that actually I'm digging into these two questions down here. So, number one, write an equation relating the pulling force and the weight. Okay. See what equations like this are good for is, see what if the next class comes in and you leave this lab paper on your desk? They should be able to predict. They should know, well, if Griffin pulls this weight, I should be able to predict what the pulling force is going to be. Or what if I break out like a huge old weight, right, and attach a big spring scale to it? Could you predict what the pulling force is going to be? Well, if it's paper and paper, you should, because we have a relationship. Right? It's a direct relationship. It's going to be, looks like 0.31 times the weight, where 0.31 represents the coefficient of kinetic friction. Okay? Yeah, so if you know the weight, if you multiply that weight by 31%, you should get a pretty good idea of how much pulling force I need to put on it. Right? You guys got the idea? Right? And then what does mu represent in the equation? You could say, well, obviously it's a coefficient of kinetic friction. But actually, here's a better answer. Here's really what I'm looking for. It's the slope of the line, right? And that's why I labeled the slope as mu, or mu sub k specifically. This is the sliding friction. Okay. You guys good? Good there? Any questions on that half? All right, you guys ready to switch over to a completely different way to think about friction? All right, so here's what we're going to do. Well, let's take a look at this table, see if we can make sense of this. Right? We're going to have different trials. I'm going to choose different weights. Here are my weights that I've wrapped in paper. Oh, and the big guy. It's got these different paper wrapped weights. Okay. Okay, now there's some angle in degrees. Now, I didn't specify this here, but I should have. This would be relative to the horizontal, wouldn't it? Okay. Maybe you want to write that. You say relative to horizontal. Okay, so a flat plane would be 0 degrees to the horizontal. Okay. And then I'm going to have you guys take the tangent of that angle. Now, why am I having you take the tangent? What does this have to do with friction? Let's gather the data first, and then in the analysis, I'll do a free body diagram that should look hopefully somewhat familiar and make sense of it from there. Right? You guys ready to go? All right, let me switch my camera angle. That's okay. Okay. We bump up the pace a little bit, just make sure you guys got time of class too. Yeah. Okay. So remember, pick one of these two ways of measuring friction and do a write-up. You don't have to do write-up for both, just pick one. Okay. So let's start with the little guy. Okay. Let me grab my data real fast. You guys write it down and try to save a minute maybe. Okay. So the little guy is 0.5 newtons. Oh, actually, just copy paste the weight values because we already measured those. Okay. 1.0, 2.0, 5.0, 10.0. Right. Since we already measured those, let's just save some time. Right. So you guys online, see, I just copy pasted the same weight values that I had before. Okay. All right. What is the angle that this thing's going to slide down at constant velocity? Can you guys see I taped some paper on this desk? So you guys see, okay. Yeah, I taped some paper here. So I can have paper on paper technology. So same ideas before. Right now, the desk surface is pretty close to 0 degrees. I'm gonna hang this protractor so it hangs level. You guys see it's like level with the ground. Okay. And I'm gonna see where does this break friction and start sliding. Okay. So right now, it's stuck, it's not moving. Air hockey cable would already be gone. Okay. But here we go, and come on, little guy. Right. Now I got it up to an angle where see for it to break friction, it looks like it's sliding down faster and faster, kind of like the car. Right? So the initial angle to break the initial friction, does that refer to kinetic or static friction? Static. So really what I have to do is, once I break the friction, I actually have to tilt the table back a few degrees, like taper off, to get it to slide down at constant velocity, and that's the angle I'm interested in. True? Okay. So let's see if I can get it to slide down at constant velocity. Maybe I give it a little tap. Whoop. Right. That's pretty close, right? Yeah, I'm happy with that. That's pretty close. Let's see what this angle is. I'll do my best at getting this angle. Okay. So I have 2 points on this desk edge. One goes through the node, the other goes through 20 degrees. I'm looking at 20 degrees. 20. Okay. That's your first angle, 20 degrees. Okay. Now let's bring in the next guy up, the 1 Newton guy. I know he's 1 Newton because I measured him already. Did I show you guys how to use the triple balance beam? No, didn't do that. Okay. Let me show this to you guys real fast. This is an old way of measuring mass specifically. So it's got these scales. You guys may have maybe doctor's office seen something like this. Right? So no, this goes through torque to measure it. It tries to balance it. Right? Torque is like opening a door. It's like swiveling it. There's like a swivel point. Right? Now this actually truly does measure mass. This should be really close to 100 grams. Yeah, it's really close to 100 grams. Right? So for this to balance out, maybe like 99 grams, something like that. Now this is much more precise than the spring scales are. Okay? But guys, if I took this to Mars, would it give me the same mass? It sure would, right? Now it needs gravity to work because there's a weight here and a weight here, but gravity ends up canceling out with like a seesaw. Right? Yeah, if I took it to Mars, I would still get the exact same measure of mass. Right? Anyway, so back to our main experiment. So for this guy to start slide down at constant rate, ooh, they're sliding down at constant rate, pretty close to. Kind of got stuck there. That's pretty close right there. I'm gonna go with this angle. Okay, get this angle. This looks like 23 degrees, I think. 23. 23 degrees. Next guy up. This guy. The 2 Newton weight. That's pretty close, isn't it? Whoop. Well, that was it. It was going constant velocity down there. Let's see what this guy is. It's going at 20 degrees. I'm reading 20. 20. Right. This guy's online, as we are so far. Right. The 5 Newton weight. That's pretty close right there. Call that my angle. All right, let's see what this guy is. Hold this level. Here, try this again. Okay, try to hold this right here. And it's about 25. 25. And then the big guy, the 10 Newton weight. 1 kilogram, 10 newtons. Oh, is that already? Yeah, that's pretty close to constant speed, isn't it? Okay, guess I like that angle. Let's see if I can get this. It's about 22 degrees. 22. Right. My camera back. All right. All right, so I want you to take the tangent of each of those angles, make sure your calculator's in degrees. Now, I haven't told you why tangent yet, but maybe some of you guys figure it out. Does anybody think they figure out why I'm having you guys take the tangent of the angle? I will show you a free body diagram analysis. Let me grab the average of these. Average, I'm getting 0.402, 0.40. Okay. All right, now, why am I having you guys do tangent? Right, you guys ready for this? Okay. So it's something to do with an incline. So let's get an incline going. Some angle theta. Okay. There's a block here. Okay. Let's do a free body diagram, FBD. Free body diagram. Okay. Now I know one force on this is obviously its weight. Now gravitational weight pulls straight down. Label this mg. Okay. I need to introduce a Cartesian system that runs parallel perpendicular to the surface. That's always one of your steps for your inclines. Okay. Because most of the forces are aligned along that. Okay. Of course, the weight I would have to break up into components. You guys remember that? So let's break the weight into components that are parallel perpendicular to those axes. Okay. Now, obviously, this one runs along the axis. You guys see I'm going to draw this one, this component down here, as parallel to the surface. You guys see how this line and this line? Well, I have to do that. This line and this line are parallel. See how they run parallel? You see that? Okay. So this angle theta, same thing. That makes this mg sine theta. mg cosine theta. You guys getting pretty comfortable with that, right? I've got a normal force, which is equivalent in magnitude to mg cosine theta, wouldn't it be? Okay. And then finally, to keep it in equilibrium, wouldn't I need a friction force that is equivalent in magnitude to mg sine theta? Squeeze that down here. Mg sine theta, right? You guys get that? Okay. Now, the last lab setup that we did, we were saying that the coefficient of friction is the ratio of friction force to normal force, right? It's like the drag force compared to the weight would be equivalent to that. Okay. The new way we're thinking about it has something to do with this incline and this angle. Let's pop in some values for this. Friction force, isn't that equivalent to mg sine theta? Mg sine theta. Normal force, isn't that equivalent in magnitude to mg cosine theta? Mg cosine theta. Does mg cancel out?
Yes.
Yeah, so over and over, we're getting about the same angle for each of the weights regardless. Okay. What if I took this to Mars? Would they also break at the same angle on Mars? Yes, they would, because gravity cancels out. Now, you need gravity to make this work. But once it's there, it doesn't matter what the magnitude is. Anytime you see a variable cancel out, it means that the magnitude of that thing makes no difference. Guess what is sine divided by cosine? Tangent. Look at that. Mu is equal to tan theta. Ooh, right? No, the initial break angle would refer to mu sub s. The constant velocity slide angle is mu sub k, and we're interested in mu sub k. Okay? But same analysis for either one. Okay? Tan theta versus weight. Let's throw weight down here in newtons. It went up to 10, so 0, 2, 4, 6, 8, 10 newtons. The tangent of the angle, well, the biggest value was almost 0.5, so let's go 0, 0.1, 0.2, 0.3, 0.4. Did I mess up somewhere? Probably did. 0.5. Okay, something like that. All right, so for a half a Newton weight, it came out to 0.36. That's right about, I totally messed this up, whatever. All right, close enough. 0.36 is about there-ish. For the 1 Newton weight, came out to 0.42. it's right about here. For the 2 Newton weight, it was 0.36. Which is the same as the other value. For the 5 Newton weight, it was 0.47. Right here. And then for the for the 10 Newton weight, it was 0.4. Okay. Ooh, guess what relationship you see from these dots? You see it like a flat line? That flat lines, doesn't it? Okay. In fact, it should flat line right at the average, which should be like 0.4. Because we got the average as 0.4, right? Okay. So, ooh, you guys know that flat lines, vertical lines on these graphs tell you something about no relationship. You guys remember that? So there's no relationship between the tangent of the braking angle and the actual weight. But you know that because we were getting the same braking angle over and over. Or I should say the same sliding angle. Right? So tangent theta is 0.4. That's it. There are no units because you guys know sine, cosine, tangent are ratios of things. So all the units cancel out. Right? And then how does tan theta relate to mu from the other side of the slab? Okay. Supposedly, mu should be tan theta. Okay. Now, how close do we get? We got 0.4 using this method. We got about 0.31 using the other method. Those aren't too far away from each other. They're not exactly the same, but they're not that far off, are they? All right. So I'll give you guys last few minutes of class to let me show those lab write-up directions back up here. Okay. So pick one of these. You don't have to do both. Just pick one. Either what we started doing with the spring scales or what we do with the protractor. Okay? And do this lab write-up. If you finish this before the bell, then you can pop that in the grade tray and you're done with this. If you don't quite finish, then you can turn this in tomorrow. Okay? So I'm looking for a lab write-up on one of those. If you got any physics questions, then I'm happy to help you out.
Mr. Grayson,
Yep.
should I refer to them as weights or specifically 0.5 Newton, 1 Newton, 2 Newton?